Yeah, so in the previous class we had sort of looked at transformers. So Zachary, I'm not sure if you remember, well, in the last class we looked at how to charge a battery. Now remind me, batteries carry what kind? Okay, batteries produce what kind of current? Alternating current or direct current?
Direct current.
Right. And so I said, in a battery, a phone battery might be like 5 volts. The voltage in your The voltage from the socket is 120 volts and is AC as well. So the procedure would be it has to go through a transformer. And what did the transformer do again?
It converted from AC to DC and bring
No,
on the volt.
no, no, uh-uh.
No.
Mm.
So the transformer,
The transformer. The transformers do.
so that though converted from AC to DC
Nope.
or bring down the voltage.
Let's bring down the voltage.
Or
The diode is what is converted from AC to DC.
all right, so
Yeah. Um, Speaking of which, I need to look at half wave rectification and full wave rectification, which you
What is it?
more than which one?
You think? No wake
All right.
up?
Now we now wake up.
Yeah.
Okay. So so Zachary, I do want you to say that a transformer transforms the voltage. So a transformer either steps up the voltage or steps down the voltage. A diode is what is actually do the conversion. So
all right,
I really need to explain that to you. So let me show you how that work. So I'm gonna do something. We need to look how diodes work, right? Diodes. That was something I'm supposed to go through, but I forget. So what does a diode do?
convert from AC to DC.
Exactly. And you know the working principle of a diode?
To keep the current flowing in one direction.
Exactly. To keep the current flowing in one direction. So let me ask you a question. Let's just say, for instance, that we had this circuit over here. So a diode only allows current to flow in one direction. And the type of diode we'll be using is a semiconductor diode. But all diodes be typically work the same. Exactly. When you hear the word semiconductor, what does semi mean? Half. So it's only a conductor half of the time. If the voltage is negative, it won't conduct. All right, so only allows current to flow in one direction. And when it flows, what bias do you call that? Forward bias or reverse bias?
Forward bias.
Okay, you guys remember. That's good. Forward bias. Nice. And this is what a diode looks like. So in this instance, oh, I want you to think of a diode like this, right? So you see how it kind of looking like an arrow?
Yes,
Um, Forward bias would be in this direction. You see that or not?
yes, that's even.
So if the current is flowing in this direction, the diode is gonna conduct and it's gonna allow the flow of current. But if you reverse the polarity and the current is going in the other direction, it's going to be blocked. So what do you call that?
Reverse bias.
Right. So forward bias is the flow current, and if it's in the other direction, it's not going to conduct. So as you can see, it's only conducting half the time. It's not conducting all the time. So it only conducts in forward bias.
Yes, sir.
So the first thing we're gonna look at is a half wave rectifier. When you hear half wave, that sounds like you're working for the full thing only half of the time.
Half of the time.
Right. And that's the whole concept here. So I'm gonna pass circuit here with a AC power source. If you recall, we represent our AC power source by drawing this sinusoid over here. So this is our AC supply. Do you remember what the graph would look like? Do you remember what the VI graph would look like for this? Or the IT graph? The current versus time graph. How would it look like for AC supply? Would it be a line or would it be a sinusoid?
A line.
Yeah. If it's a line, okay, I'm asking a question, right? What is AC current? That's the first thing I should ask you. What is AC? What does AC mean?
Alternating current.
So is the current fixed?
No, sir.
So if the current is fixed, would it be a line or would it be moving up and down, up and down?
You're moving up and down.
Exactly. So for AC supply, it'll look like that because the current fluctuating. Like
Oh,
what the,
it's it.
like the current in this direction 1 minute and in the other direction, it's switching. Remember, your alternating current mean that the direction of the current switches periodically. We have the diode here. Just we have our resistor here. So guys, here's the scenario. Let's just see um at t is equal to 1 second, the current is flowing in this direction. So right now, it's in what? Forward bias or reverse bias?
Forward bias.
But Jaden, if it's an alternating power source, will the current always be in that direction?
No, it'll be in reverse bias.
So let me just say at a different time, let me just say we have a time of 2 seconds, right?
Yeah,
And at a time of 2 seconds, maybe the direction of the current would switch.
yeah.
So if the direction of the current switches, maybe it might look like this. Will it be able to complete the circuit?
No,
No. So this is forward bias, and this is reverse bias. So, Zachary, if we were to draw a graph for the current going through the resistor, tell me, would we be conducting current for the full 360 for the full period, or would we only be conducting current half of the period?
Half of the period.
Right. So let we understand what happened, right? So you see this over here, Zachary, you see where the current is passing through?
Yes, sir.
Right, this is called the positive half cycle. This is the positive half cycle. So there's the positive half cycle where it's in forward bias. What do you think we'll call it in reverse bias?
The negative half cycle.
Right, so the negative half cycle. Okay, and if you are confused, watch, this is the full cycle. So we have the positive cycle here, and we have the negative cycle. So positive half cycle and negative half cycle. All you understand?
Yes, sir.
Right, so Jaden and Ryan, will it conduct in the positive half cycle over here, or will it conduct in the negative half cycle over here? One or two? Where will it conduct?
Be positive.
Exactly. So let me ask you that question. The graph, so if we're talking about the current passing through the resistor, hence the current would only pass through the resistor if it is in forward bias. So what I'm trying to say is the graph might look a little something like this. So it will conduct current here. Tell me, for the negative half cycle, is it going to conduct any current?
No.
No. So that's going to be blank for some time. And then it's going to go, the direction of current going to switch back and it's going to be positive again. But you notice in half wave rectification, what's the problem with that? Let me see if I can identify a problem with that.
It always work.
I mean, it is work, you know. It is work. It's just that does it work all the time?
No.
Tell me, Zachary, Jaden, and Ryan. Like, if you notice, we have some downtime over here. And normally you would have the negative half cycle there.
Yeah.
Yeah, but because of the diode, it's not gonna conduct during the negative half cycle. So the resistor, sometimes the resistor with no current to pass through the resistor, none. You understand? So,
Yes, sir.
so I can put it like in a dot, so you can know that this was here. So diode only conducts. Zachary, do you want a power supply that did like this?
Nah, sir.
Why?
Because it wouldn't be supplying current all the time.
Yeah, then there's a problem.
Yes, sir.
Ryan, would you want a power supply that like has a downtime? It working 1 minute, then it stop, then it working the next minute, then it stop, then it working the next minute. You want that?
No, sir.
No. So I'm gonna explain this in one more time. In a half-wave rectifier, you are using one diode, and the purpose of a diode is to only allow the current to flow in one direction. So as you know, in an alternating current source, the direction of current is switching back and forth. So 1 minute, it will be in forward bias, so the current will pass through the resistor here. In the other minute, the direction of current will switch. And if it switches, it's going to be in reverse bias now and is not going to allow current to be conducted. And so that's going to form a short circuit. I mean, a open circuit. So what I'm trying to say is, during the positive half cycle, you'll conduct current. During negative half cycle, that's going to be in reverse bias and the diode is going to block the flow of current. And then the direction of current is going to switch again and it's going to be in forward bias, so it'll conduct. But there's clearly a downtime. So, Zachary, are we conducting the full cycle or only half of the cycle?
Only half of the cycle.
Yeah, so would you say that's efficient or inefficient?
Inefficient.
What about the rest of you guys? Would you also say that's efficient or inefficient?
Inefficient.
Yeah, that's definitely inefficient, right? So it's only conducts during the positive half cycle. So clearly there must be something better, right?
Yeah.
Yeah, there must be something better. Come on. So let me show you guys what's better. So if a halfway rectifier does only conduct half the time, what do you think you'll call the proper thing? That's work.
Just a rectifier.
Say that again?
Just a rectifier.
Nah, full rectifier. A full wave bridge rectifier, let's call it. Right? So full wave bridge. Right, full wave bridge rectifier. Any guesses as to how much diodes this would use? It's not just gonna use one diode. Any guesses? So how much diode this might use? Taking those I know.
Two?
Two, nah, four. Quite a lot. All right, we'll work with that. I bet. So we have this here. And we are going to connect this in such a manner like this. Okay, only with me so far. I have four diodes, right? In this particular direction. The direction is very, very important. If you mess up the direction, you'll get it wrong. Guys,
Yes.
Yes.
cool. So you connect the AC power source in this manner, and to get the output will be given via these two terminals here. Yes, so you get any output over here. So in the middle, I'll put a resistor, a load resistor. And the purpose of the load resistor is just to show you, like, do you guys know all components have like a certain resistance? Or not?
Yes.
Yeah, all components have a certain resistance. And so I just use an resistor to indicate that is a resistive load. All right, so let me explain something before I continue, right? Guys, question. Would you all say that this is alternating current or direct current? After halfway rectification, does it give you alternating current or direct current?
Alternating current?
Nope. Dylan, does the current ever dip to negative?
No.
No. So does the direction ever change?
Right.
Think about it, Jadon. Isn't over here positive current?
Yes,
Does diode ever allow it to conduct negative? Or in the
no.
negative? No. So
No, it
this is
just
actually, so the halfway, to the one diode actually converted what to what?
converted to positive.
They
It is
converted AC to what?
to DC.
Exactly. Right? Good. So that's the purpose of a diode. So AC to DC. This is AC to DC, yeah? Guys, once you're not seeing positive and negative currents, is DC. That's clearly DC. All right, so let me just go over this setup one more time. So
Sure.
you have four. I see some. Yeah, Drew.
You could scroll up and zoom out for the notes above and now join.
All right, take a screenshot.
So I had get up 8 and I didn't see no message. I just closed
What?
my eyes and next thing you know it's half past.
I gotta swear I sent that message 8 o'clock on the dot.
I didn't see it. I had other messages.
Please, boy.
That's this is
All right.
all?
Yeah, that's all.
Thanks.
So what I was saying, right, Drew? Remember alternating power source, the current goes switch. It goes switch direction. It go 1 minute it'll be positive, next minute it'll be negative, you know? Up and down, up and down. So the current graph is look like this. And so we connect it to a diode. A diode is only allow current to flow in one direction, right? So maybe at one instance in time, the current flow in this direction. There's in forward bias. Yes, it will conduct. But you know, it's an AC power source. So next minute, it might switch direction. The current might switch direction. Will it conduct in this direction?
No, sir.
No, that's in reverse bias. So what I'm saying is the graph will look like this. It will conduct during half of the cycle. During the negative cycle, it's not going to conduct, that's the downtime. And then it's going to conduct when the direction of current switches again. So, yeah,
So it will conduct no current during the downtime.
no current. So there's a problem with this. Do you want to use a power supply that is only work half of the time?
Nah.
No, you wouldn't want that. But it's a very crude instance of converting AC to DC, right? So this is called half wave rectification because you only conduct half of the wave. Right. Now we're gonna look at full wave bridge rectifier. A full wave bridge rectifier. It rectifies the whole AC signal. Right, so Zachary, ready to see how this is work?
Yes,
Okay. Let me see if I get animation. So it's a bit harder to explain. In school, they're just gonna hang this diagram until I remember it, which is lame. All right, so let me go. All right, so Zachary. So guys, pay attention. Let's just say, at a time of 1 second, the current is flowing in this direction. Question, guys, would the current go in this, would the current go here or would the current go here? One or two? What do you all think?
They wouldn't go both ways.
Yeah, it would go both ways. Zachary, pick up on that boy. Guys, over here we have a junction, right? So any current would split at the junction.
Yes, sir.
So if the current splits at the junction, right? So stay with my guys. The current is gonna split at the junction, but you have a diode over here and over here. So tell me, guys, talk to me, right? Talk to me. Will this diode allow this current to flow there?
Both side.
No, so it blocks it. Will this diode allow this current to flow in that direction?
Yes, sir.
Mhm.
Right. So that current flows and it goes to the load, right? Because
Yes.
you're hooking up the load over here. So like imagine you wanted to charge a battery, you go hook up your battery to these terminals, right? Okay, cool. So guys, can we see that it is conducting current during the positive half cycle or the scene there, right? Like when it's in forward bias, current is being conducted,
Yes, sir.
right? Current is being conducted. Cool. And it'll go to the load. Nice. A little bit more now.
Yes, sir. You get you.
Yes, sir.
All right, cool. Give me a second. One moment. Yeah, so guys, if I could, I'm gonna continue, right? So you all understand the current is gonna go through the resistor now, right?
Yes,
And
sir.
then the current is gonna encounter this junction. And the junction, what the current is gonna do?
You split.
Can the current, well, the current could go in either direction, right?
Yes, sir.
Okay. But the main one we're looking at is over here. So the current is gonna go in this direction. Can you all see that this diode will allow the current to flow there,
Yes, sir.
right? So does it complete the circuit? Does it
Yeah.
come?
Yes,
All right.
sir.
So I'm gonna go over that one more time. So let's just say at a point in time, the current is flowing in this direction, right? So the current flowing and flowing and flowing and flowing. It reaches this junction and gonna split. Can I go both ways?
Yes, sir.
Yeah, it could go both ways. Will it be able to go here?
No.
No. Right. So it has to go here then. So it goes here, right? Um, it has a junction here too, right? So technically you could say it could split, right? But can I go through this diode?
No.
No, sir.
Let me say, can't go through the diode. So the only way it goes through is so where's the only path that current could take? What's the only path the current could take there? Through the what?
Through the middle.
Through the middle. And so it's gonna flow through the resistor. And at this junction here is gonna, well, for the purposes of understanding it, it's just it's gonna flow through the last style there, right? I mean, if you think about it, like here, it'll just, I mean, it'll just continue, it'll just continue, right? So we could ignore that. So over here, the current is gonna keep flowing. Are you all seeing that the current is gonna keep flowing and it's gonna complete the circuit? So do you all understand that instance?
Yes, sir.
Right. Let me look at the current flowing in a different direction now. So Drew, let me look at the current going in the other direction. So in this diagram, so tell me guys, did the current go through the load in this instance?
Yes, sir, it did.
Right. So in the positive half cycle, it conducted current. Okay, so Drew, the other direction would be like this. This would be the other direction. So tell me, Drew, what is this? What's that called?
Junction.
Right, so the current was split at the junction. Drew, can the current pass through here?
No.
Nah, so it's blocked. Can the current pass through here?
Yeah.
What is this?
Next junction.
Right, so the current will want to split, right?
Yeah.
Current pass through here.
No.
So where does it end up going instead?
The resistor. Pink line.
Exactly. So you have current flowing through the resistor, right? You have current flowing through the resistor. Now, over here, you have a junction, and if it were to split, the current would just come back, which is the whole, like, well, I'm gonna continue, right? So the current, watch this for yourself, right? So Drew, at this junction over here, the current would split, right?
Mm-hmm.
Um, but we're gonna ignore this for now. Like, we're gonna ignore that for now. And we're just gonna look at the return part. So the current, can you see that the current is going to return back? So you'll complete the circuit.
Yeah.
Yeah, I hope you can see that. So at this junction over here, we're gonna ignore this for now. At this junction over here, you can see that the current, it's gonna flow and it's gonna continue the circuit. Bam. So talk to me, guys. That was during the negative half cycle. Did we conduct current during the negative half cycle? Talk to me, guys. Did current pass through the resistor during the negative half cycle?
Yes, sir.
Right. So as you can see, we are conducting current for what? Half the cycle or both cycles?
Both cycles.
Yeah. Now let me explain this. I really don't want anybody to be confused, right? We have a current in this direction and we have current in this direction. What are they? If you have currents in different directions, what happen? What do you think? Think about it. What are they gonna do to each other? If you have currents in different directions. Come on, guys, think. If you have +5 and -5, what happen?
They'll cancel out each other.
Yeah, so you'll have current cancellation here via superposition. So it'll cancel off. And say the current just ends up flowing through there, really. So in this branch over here, the current just cancels off. Yeah, the current just cancels off. I'm not sure if all is seeing that, right? Because like, wait, watch. Drew, you're gonna have current flowing in that direction there, and you're gonna have current flowing in this direction here. But it's from the same source, Drew. It's from the same source. So it's gonna have the same current, but just different directions. So you come like a vector. If you have two currents in different directions, what happen?
They'll cancel out each other.
Yeah.
Wait till you get show me again how you get two currents coming in the same direction.
Okay, no problem. So let's look at the whole diagram again. All right, so Drew, now we're looking at the negative half cycle, right? So guys, pay attention, right? I want you all to get it. So, Drew, do you understand that the resistor here is a load, right? Like that's where you go actually. So, like, let me explain something. Drew, when you're charging your phone, right? Do you think your phone, okay, we have in your phone, what is power your phone?
The battery.
Right. Do you think the battery produces alternating current or direct current?
Um, direct.
Exactly. So you need direct current to charge your phone. But the power socket in your home, that does give you alternating current. So your charging block has a transformer in it. The transformer reduces the voltage, obviously, 120 volts will kill your phone battery, right? The transformer would drop the voltage, then the diodes would convert AC to DC, and that would charge your phone. So what I'm saying is, you see these two terminals over here? Those
Yeah.
two terminals is where you would connect to your phone. So after the rectification, that would convert the DC to AC. Oh, I say, sorry, that would convert the AC to the DC. Yeah. You understand? So like we have AC over here. After the rectification between these two nodes, you'll get a DC current. You understand?
Yeah.
All right. So Drew, we looked at this direction, right? So the other direction would be this. Yeah?
Mm-hmm.
Cool. So stay with me. Guys, I want you to understand this. Not just like memorize it, but actually understand what's happening. So Drew, at this junction over here, what happened to the current?
You'll split.
Cool, it will split. Um, you understand that?
Also, I see it now. Don't worry.
All right, cool, cool. So this will be blocked, but the current will be allowed to flow in this direction.
No.
And so that current will end up reaching this junction over here, and that current is gonna split. Will that current be able to pass through this diode?
No.
No, so it's blocked. So the current ends up flowing through the resistor in this direction. Yeah?
Yes, sir.
When it reaches this junction, that current is gonna split. So it's gonna go over here and it's gonna go over here. Now let me ask you a question. Isn't that in forward bias so the current go pass through?
Yeah.
But when the current passes through, what happen here?
They'll cancel out.
They'll cancel out because of superposition. You have equivalent currents just in opposite directions. So think about it like vectors. They're gonna cancel out. You understand?
Yes, sir.
So the current continues flowing here and it completes the circuit. Let me know if you're seeing that.
Yes, sir.
And you're probably saying, but sir, and the current goes split over here? And the current goes split over here, like technically it's supposed to split.
Mm-hmm.
Okay, well if the current splits over here, right? Yeah, it would go through the diode because it's in forward bias, but when I reach over here, what happen?
It'll cancel with the
Exactly.
other.
So the only path current really gets to take is through the what?
Through the well, the pink line.
The resistor, the load resistor, as a resistor. So this is the part where I blow all your mind. So during the positive half cycle, look at the direction of current that flow through the resistor. Are you seeing the direction of current that flow through the resistor?
Yes, sir.
Watch this. Bam. Look at that. It's
Ooh.
the it is in the what? It's in the what?
Same direction.
Yeah. So whether it's the positive half cycle or the negative half cycle, the full wave rectifier uses a clever trick. It uses the fact that current splits at a junction, as Zachary would have noted. So Zachary, and when the current split at the junction, it will take like the direction go kind of it's like a kind of fast move now. It's like kind of uh it's a kind of a scheme or something. Like you see now, like the current would go over here and here, right? So like basically the diodes channel in that, and it's allowing the current to flow in the direction you want. So
Yes, sir.
let me know if I catch that.
Yes, sir.
So I'm gonna go over the positive half cycle one more time. All right, so Zachary, the current gonna flow right in this direction. At the junction, what the current gonna do?
You're gonna split.
Right, so you're gonna split in the middle. Where is the current gonna be able to pass through? One or two?
2.
Right. It is in reverse bias here, so the current wouldn't be able to pass through. However, the current will be able to pass through this diode, and so it's gonna keep flowing. Right, Zachary, when you reach this junction over here, what happen?
Current gonna split again.
Right, the current gonna split again. Can the current flow in this direction?
No, sir.
No. So where does it flow then?
3 resistor.
It flows through the resistor. The current is gonna split at this junction here, right?
Yes, sir.
Well, let me ask you a question. Yeah, isn't it in forward bias so you can pass through that resistor?
Yes, sir.
But when it pass through the resistor, what are you gonna encounter?
And another direction of current.
So what happen?
They will cancel off.
They'll cancel off, right? So you end up with no current flowing through in this node. No current.
Yes.
So the current only ends up going in this direction. And if that is the case, you notice that it gets to complete the circuit.
Yes, sir.
So let me just simplify this. So guys, in the positive half cycle, do you guys understand that this is the path that the current takes?
Yes, sir.
Like if we ignore any fluff, right? All you understand that there's no current flowing through these nodes, right? None, 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 none.
Yes, sir.
Yes, sir.
And if we look at the other one, then what do? Tell me guys, would current flow in this direction?
No.
No. Would current flow in this direction?
No.
No. It's gonna flow through the resistor. Is current gonna flow in this direction?
No.
No. And the convenient thing is, in both instances, the current that goes through the resistor is in the same one.
Same direction.
Yeah, that is the convenient thing. Let me know if I catch that. Can you all see that in both instances, the direction of current flowing through the resistor is the same?
Yes, sir.
Yes, sir.
So, no matter the half cycle, the direction of current through the resistor is maintained. In other words, it creates a perfect DC current. So, like, let's look at the waveform now. Let's look at the waveform. So, this is current versus time. So, during the positive half cycle, will it conduct?
Yes, sir.
Now, let me ask you a question, right? In an alternating current source, doesn't the direction of current switch back and forth?
Yes, sir.
So, you would typically draw this. But let me ask you a question. The four diodes did what to the direction of current? So, like, watch. This is the positive half cycle. Look at the direction it's going in. And this is the negative half cycle. What? Did the direction change?
No, sir.
Drew, Ryan, did the direction change? The direction through the load. The direction of current through the resistor, did it change?
No, sir.
No. So if it didn't change, am I going to do this or am I going to do this? One or two? What do you all think?
2.
Ryan, Drew. So like you see in here that the direction of the current it never changed. It did never change. It continued going in the same direction. So will the sign for the current change? Okay, remember, In currents, the sign indicates direction, right? So if it's positive, it's in one direction. If it's negative, that means that the direction of the current switch. So I'm gonna ask you a question. Drew, does the full wave rectifier allow current to change direction, or does it go the same direction through the resistor?
There's the same direction.
Same direction. So will the current ever go in the other direction?
No.
No. So would the graph look like that, or would it look like this? One or two?
One.
One, yes, yes. Precisely. So can you guys see that for all of the waves, it's conducting?
Yes, sir.
Do you guys understand that? They surely understand that.
Yes, sir.
Right. When you learn this in school, I know your teacher just gonna give you this until it's a memorizer. I know, I know. Sad times, boy. But at least I'll let you understand how it is work. Right? If you draw the currents, you'll see how it works. Now, which half cycle is this? The positive half cycle or the negative half cycle?
Positive.
So it conducts during the positive half cycle. Um, Jadon, which half cycle is that? Positive half cycle or the negative half cycle?
The negative half cycle.
Right, that's the negative half cycle. So no matter what cycle it is, the direction of current going through the resistor remains the same. And so, hope that makes sense. And this is the positive half cycle again. Right? So by doing this, we converted what to what? Tell me.
AC to DC.
DC to DC. You mean AC to DC? I think you said DC to DC.
Says AC to DC.
Yeah, AC to DC. So which one of the thing is being on the phone? The halfway rectifier or the full wave rectifier? What do you think? Like to charge your phone now, what do you think? Which one is being on the phone?
Full wave rectifier.
Yeah, obviously. Now, if you notice though, there's still some dips in power though. Are you seeing that? Like there's still some dips.
Yes, sir.
So maybe it would be nice if there was some way to store energy between cycles. Do you all know any device that could store energy for like a short-term period of time? Don't say a battery, eh? A battery to store charge for a long period of time. What is store charge for a short period of time? Do you all know? You learned about resistors, you learned about diodes. Are there any other electrical components that store charge for a short period of time and then discharge?
Light bulbs.
Capacitors.
Capacitors. Yeah. Yeah. Oh, yeah, 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 yeah. Capacitors. What does a capacitor sound like it does? Guys, what does that capacitor sound like it does?
Hold some capacities, sir.
Say that again?
Or like a certain amount or something.
Exactly. It holds a certain amount, right? Yeah. A little bit more like a little confused.
Now see with you.
Okay. Give me a second. Just reply to a message. Yeah, yeah, all right. So cool. Do you guys think this is the most optimal power supply? Talk to
Well,
me, yes or no?
no, because it had the dips in power.
Exactly. So we're gonna move on to something called smoothing. Right? So We're going to be looking at the smoothing slash ripple capacitor. So I don't know what a capacitor does look like.
Oh shit.
It's like a little battery. For sure. Yeah. Is that just in the ACN thing, you know? There's a bunch of capacitors, bunch of types. All these are capacitors. And the ones in the air condition, just look like this. Have you ever see that before in your life or not?
I see.
Ah,
I see small ones.
small one. Yeah, the air conditioners have these. All right, cool. So let me do some explaining. So the capacitor acts as a short-term charge storing device. Short-term, and it stores charge via two different plates. So short-term, why my brain gone blank, me? Charge. Yeah, short-term charge storage device. What does this mean? Well, if I tell you it's a short-term storage device, I think you can store charge for a long period of time.
Nothing.
No, this is only store things like in a couple of seconds, right? It has a really fast charge and discharge time. So like what that means is it would discharge fast and it would also charge fast. So fast discharge and fast charge. You know what discharge means?
To lose charge too.
Yeah, to like offload your charge to a component. So a capacitor is a short-term charge storage device. It stores charge for a short period of time. I don't know what else I could say. That's literally what it does. And you would place that, like, let me show you the improved power supply. So what you would do is you would place a capacitor. You'd actually place the capacitor um in parallel to that. Yeah. So let me just change this up. So between these two terminals, you'll get what kind of current? Alternating current to direct current. What some of us? Between these two terminals, what you get?
Direct current.
Yeah, you'll get direct current, right? So what you gonna do is you got higher resistor here, and that's your load. This is your load, right? So you connect something here. Cool. That's your load. One of these gonna be positive and the other one gonna be negative, right? Cool. That's your load. And what you would do is you hook up a capacitor parallel to it. And you see this over here, this is a capacitor. So what does the capacitor do, guys? Well, between cycles, the capacitor would store some charge and then it would discharge. So it allow it to be a bit smoother. Because let me explain, Jadon, from here to here, and there's like a gap.
Yes, sir.
So what the capacitor would do is the capacitor would start to store charge during this time, and when it's a downtime, it would discharge and it would basically the capacitor would give charge during the downtime to allow for like a seamless transfer. That makes sense or no?
Yes, sir.
So with the capacitor, you're gonna end up looking like this. What looking better, that or the other one? Watch. So you're gonna end up with something that looks like this. Doesn't this look more or less like a line, like a actual DC?
Yes, sir.
Yeah. So I'll probably understand. And these things over here that they are the smoothing slash ripple capacitors in effect. And you see this thing over here, what you call it? What you call this? That weird symbol over there. What's that, guys? Take a look.
Battery.
To that again?
Battery.
No, it's not a battery. Nah. Let me ask
No.
that question. Would a battery wouldn't be useful here, no, Jadon? Does a battery take a short period of time to charge or a long period of time to charge?
A long period of time to charge.
Then you want something that is switch. Okay, like I'm asking that question. You think all right, so let me explain. The alternating so alternating current means that the current switches direction, right? Yeah.
Yeah. Yeah.
The type that you have in your main socket, it switches direction 60 times per second. You feel that's a lot of time to charge and discharge?
No.
No, you think a battery could charge and discharge in 1/60th of a second?
No.
No. So you use a capacitor then. A capacitor discharge and discharge real fast. So you'll use a capacitor, right?
Yes, sir.
Not a battery. A battery is a long-term storage device. I mean, a long-term charge storage device. So this little symbol over here is a capacitor. No, I see that looking real similar to the battery ends.
Yeah.
Yeah, but nah, it's a capacitor. Notice that both of the terminals are the same size.
Yes, sir.
All right, cool. Right? So what's the purpose of the capacitor? Let me give you a little note about it. So it charges during voltage peaks and it will discharge when what? And discharges
When voltage drops.
yes. Right? And discharges when the voltage drops. To maintain a steady DC output. Yeah. Are you okay with that?
Yes, sir.
Yes, sir.
Cool. So we just looked at rectification and the purpose of a diode and a capacitor. Nice. Cool. Let's move on. Take out a screenshot and move on.
Yes, I get.
All
Yes,
right.
sir.
Have it?
Yes, sir.
All right. Nice. Now we're gonna move on to finally gonna move on to electromagnetism. Right. So magnets. Do you know how magnets work? Talk to my guys. Do you all know how magnets work?
Yes, sir. Kind of.
Right. So yeah, a magnet has a north and a south pole, right?
Yes, sir.
They could either okay, they could either do what? If you have two magnets, they could either be attracted to each other or they could do what each other.
We tell each
Right,
other.
check.
Repel each other. Good. So a magnet has a north and a south pole, right? A north and a south pole. So question, guys, if I have a magnet here and I have it in this orientation, what would be felt by those two poles there? Attraction or repulsion?
Attraction,
Anybody can tell me why?
because it's two different poles.
And you know what they say, Ryan, opposites attractants, and they say that?
Yes, sir.
Yeah, that's what they say. So attraction. But Ryan, if I had a north-south, right? Take this and I switch it around, like so. What got happen here?
The repel.
Right, so this could be repulsion. Nice. So we can understand how magnets work already, right? The only thing you all will learn is the magnetic field lines. And I will teach you guys about magnetic flux as well. Right? So we need to look at magnetic field lines. All right, so everybody okay with that first part?
Yes, sir.
Yes, sir.
And guys, will a magnet attract plastic?
No, sir.
No. Will a magnet attract metal? Like iron. Will it attract iron?
Yes, sir.
Right. The reason for that is actually iron actually has a bunch of tiny magnets in it. It's actually paramagnetic. And when it gets in magnetic field, it's going to cause all of the dipoles to actually align. And that's magnetic induction. Because, like, let me explain something, right? Let me explain what has actually happened. Guys, stay with me. A magnet actually magnetizes iron. Did you all know that? It actually magnetizes the iron. So for a, like, all you ever question, right? All you ever hook up a magnet to a piece of iron, and now the iron acting like a magnet. It could like the iron go attract things.
Yes, sir.
All you ever do that? Like Jaden, you ever play with magnets before?
Yes, sir.
So Jaden, like you ever have a piece of a magnet here and like the iron bar, whatever, it's attached to it, and now things being sucked to the iron?
Yes, sir.
Right. So what you are doing is you're magnetizing the iron. The process through which, so like, let me explain. Let me see if I get a diagram. Let me show you. Can I jump in the gun here? But this is fun stuff. Um, right, so I just said paramagnetic. I use that inconclusively. My bad. Yeah, so let me explain. All materials have a magnetic spin. They have magnetic spin dipoles. So that's this over here. Right? So like all materials to some extent, they have this. Ions have it a lot more though. Right? Because ions are ferromagnetic materials, right? Ions are ferromagnetic materials. So stay with me. So what I'm saying is, in the iron, like if you were to look, like you wouldn't even see it, right? But what I'm saying, Jadon, is that in iron, you have a bunch of these like small magnetic spin dipoles. And under normal circumstances, all you notice that the small magnets in the iron are look at them. Are they organized or like what? Are they just like in a bunch of random chaos order?
It's scattered.
They're scattered. So let me ask you a question. If they're scattered, do you think they would cancel off each other, or do you think they would produce a strong magnetic field?
They will cancel off each other, sir.
Yeah, so like iron by itself is just unmagnetized because all of these small magnets, the dipoles, that's what you call it, the dipoles, you learn about this in electrical engineering, that's how I know it. They just in disarray. They're not oriented. They're not oriented properly. But here what? if I take a magnet and I bring it close to this, you know what's gonna happen to the dipoles?
They'll organize.
They will organize on a line. Yeah, that's what happen. And it will look like this. See that? And it will form a temporary magnet. So like when you remove the magnet from the iron, it will take a little while for it to go back disorganized. So for a period in time, that iron will actually be act like a magnet. Yeah. So guys, when you okay, like when you have an iron bar and it's attached to some magnet, that iron actually becomes magnetic for a point in time. You know why? Because the dipoles actually align. Yeah, the dipoles align. But Jadon, if you remove the iron from the magnet, what happens to the dipoles?
They will disorganize.
Yeah, they go back disorganized, right? I don't understand the this is clearly beyond the syllabus, right? I just showing you some extra information. Right? I feel like this makes it a bit easier to explain if you know the things behind the scenes. Yeah, so like Zachary, you kind of understand this?
Yes, sir.
Ryan, you understand this?
Yes, sir.
So Ryan, under normal circumstances, the dipoles, which is like small magnets in the iron, they're in this array. They're like this. But if you take a magnet and you bring it close to the iron, the magnetic fields of the iron, or sorry, Ryan, the magnetic fields of the magnet is going to cause the small magnets in the iron, the dipoles, to align. And if it aligns, then it's going to make the iron magnetic for a brief point in time. So a temporary magnet. You understand?
Yes, sir.
All right, cool. Anybody here gonna do electrical engineering?
Not too sure.
Not too sure? All right. Cool. So let's look at the type of magnets. Obviously, they're temporary magnets and permanent magnets. So temporary magnets, they could be magnetized easily. Okay? Easily. And we just talk about it. It's a temporary magnet if the dipoles could change direction easily, right? Under the influence of a magnetic field. So temporary magnets could be magnetized easily. Do you think permanent magnets are easily to magnetize?
Nah, sir.
Nah, but when they get magnetized, it magnetizes. So temporary magnets can be magnetized easily, but they would lose their magnetism over time, as the dipoles go back in disarray. The permanent magnet, though, retains its magnetism for a long time. Let's look at the materials. So iron and Mu, I don't know what that is. That's a typo. Oh, Mu metal is a special type of nickel iron alloy. Yeah, so this just means a nickel iron alloy. Nickel iron alloy. Yeah, so like we just speak about this, right? All right, so I have a question, guys. I have a question, right? This is paramagnetic. Again, this is off the syllabus, but I like to teach my students extra stuff. 1 second. So I want to explain something, guys. Which one do you think is more susceptible to magnetic fields, paramagnetic materials or ferromagnetic? Just by looking at the dipoles, tell me which one looks like it would be more attracted to magnetic fields.
Pyromagnetic.
Paramagnetic. Paramagnetic. The ferromagnets. So like let me give you some examples of paramagnetic materials. Did you know sodium So like sodium, oxygen. Guys, did you know oxygen is paramagnetic?
No, sir.
Yeah, like guys, if you have a strong enough magnet and you have liquid oxygen, you know the liquid oxygen will be pulled towards the magnet.
Nah, sir, I didn't know that.
Yeah, let me show you. Let me show you. Show you. So the more you know. So some paramagnetic materials that most people don't know is like air, you know? Now, guys, question. Are all metals attracted to magnets? Yes or no?
Nah, sir.
No. Is aluminum foil attracted to magnets?
No.
Nah. So like not all metals are ferromagnetic. Some are paramagnetic, and paramagnetic materials have a weaker force of attraction to the magnetic fields because you have unpaired electrons. You know, one of these days I might teach chemistry. I'll think about it. Paramagnetic materials are weakly attracted to magnetic fields. So question, if paramagnetic is weakly attracted to magnetic fields, what do you think would be the case for ferromagnetic?
They're
Tell me that.
extremely attracted to the magnetic fields.
Exactly. So let me see if I get that fair. Give me a second. Strongly attracted. Ryan, did you know that air is slightly magnetic? You ever know that?
No, sir.
I'll share. Liquid air and magnet. So like if you were somehow able to, well, this is not easy, eh? This is not easy. But if you were able to cool air enough and you pour it between two magnets, you'll actually see it like bend. Let me see if I can show you. Oh, you see now, so like on either side, you have two magnets, right? And you see that little thing over there? You see that this little blob in the middle?
Yes, sir.
That liquid air. If you realize it's staying there, that's because it's attracted to the magnetic field.
Yes, sir.
Pretty cool stuff. The more you know, man, the more you know. Like, I don't know what to see in that, but like, watch. It looks like this bends towards here. Oh, you see in that? Um,
Yes, sir.
yeah, so air is actually magnetic, but nobody will tell you that. Those who don't know that. Air is actually magnetic, but like very weak, real weak. Could you all give me some examples of ferromagnetic materials? So like some materials that are really, really strongly attracted to magnets.
See what iron?
Yeah, iron is a good one. Yeah, iron is a good one. What else?
See copper?
Copper? No. I don't think copper is attracted to magnets, is it? Let me check. Nah, copper is not magnetic. Copper is actually diamagnetic. So like okay, you see paramagnetic, you see ferromagnetic. What does diamagnetic mean? So like it means that it has paired electrons that weakly repel a magnetic field rather than attracting to it. So Zachary, see how paramagnetic is weakly attracted, ferromagnetic is strongly attracted.
Yes, sir.
Diamagnetic is actually weakly repelling it.
All right, so
Yeah. So I guess I could put out here C. Yeah, so anybody could think of any other ferromagnetic materials.
Metals.
Say that again?
Metal.
No, all metals, like you see, watch. I'm telling you, copper is a diamagnetic material. Copper would actually weakly repel a magnet. Yeah. Um, and aluminum.
Cobalt.
Aluminum is a metal, but aluminum not attracted to magnets. It weakly attracted to it. Cobalt, yeah. Cobalt is one. Yeah. My second. Right, so what do you all think I should use to make a permanent magnet? Paramagnetic, ferromagnetic, or diamagnetic? Talk to me. Which one do you think I should use?
it's very magnetic.
I think so because ferromagnetic has the strongest attraction to magnets. So yeah. All right, cool. My second. I'll give it a little intro to a course in UE for electrical engineers. Magnetism 101. Yeah. Right. So temporary magnets, you might use iron, no nickel iron alloy. For permanent magnets, you might use steel or aluminum, nickel, cobalt. I don't understand that.
Yes, sir.
Yes, sir.
I'm gonna verify that because these are not my notes. I just use it because it's convenient. Would you use steel? Or ladies ever just get fed up typing and just feel like a bore?
Yes, sir.
Yeah, boy. Yeah, so like I know this was kind of sus. We don't really use steel. We don't really use steel for magnets, guys. All nickel is fine. Yeah, aluminum, nickel, cobalt is use them thing. Or we just use neodymium. Or we would use ferrite. Ferrite is just ceramic. So like guys, until like fridge magnets something.
Yes, sir.
Yes, sir.
Yeah. Fridge magnets is actually ferrite magnets. Let me ask you that question. Them magnets just feel like if it's metal?
Nah, sir.
Nah. Because it's ceramic. Is that ceramic or is that kind of what it is also do is you might like take magnetic filings. Like they might take some magnetic, so like they might create a magnet and take the particles and put it in like a soft plastic kind of thing, and yeah, that'll become magnetized in a sense. That's what they could do. Right? So when would you use temporary magnets? I ever went to a junkyard or like know what it is doing at a junkyard.
Nah, sir.
All right, so in a junkyard, and they had to pick up car parts.
Yeah.
You think car parts light?
Nah, sir, heavy.
Nah, so what they go actually use is they go actually use a electromagnet to pick it up, and then they would disconnect the power, and the car parts would drop. I'll show you guys what an electromagnet is shortly. Transformer. Did you guys know a transformer is actually a temporary magnet?
Nah, sir.
Yeah, that's why transformer just requires shielding, right? Permanent magnets, a compass needle, decor magnets, metal detectors. So you guys could take a screenshot of this. All right, so let me know when you guys are ready to move on.
Yes, I get.
All right, cool. All right, so let's look at magnetic fields now. So magnets actually create fields around them. As you can see over here, this is a single magnet. So something you'll need to remember is that the field lines always go from north to, they go from north to what?
North to south.
Remember this, guys. So Jadon, Ryan, Drew, the magnetic field lines always go from north to south. So you can see it for yourself. Watch. North to south, north to south, north to south. I think I'll get the memo, right?
Yes, sir.
And like, watch this. If you were to continue this, and you would see it, like if you were to continue this thing over here,
Yes, sir.
yeah. So like, don't let this confuse you guys. They just like cut out the top part over here, but yeah. Are they okay with that?
Yes, sir.
All right. So I want to take like, I'll gotta copy this down fast. I gotta understand this. So like if you have a single magnet, the magnetic field lines would look like that. It would go from north to south. If you had pole to pole, the magnetic field lines would go from the north to the south. If you had repulsion, it would actually look like this. You'd have a neutral point. So, Zachary, like it would repel at this instance, and you'd have a neutral point. That's repulsion. So I'd like you guys to copy this down fast. You'll need to know how the magnetic field lines behave for a magnet. Okay, so as soon as you have that copy down, let me know. I'll move on.
Yes, sir, I have it.
All right, what about the rest of you guys?
Yes, sir.
All right, cool. Hope we understand that. Let's move on. So tell me. Oh, right. Remind me, the magnetic field lines would go from where to where?
North to south.
So if I were to draw a magnetic field line like this, how would the arrow go? Would it go like this?
Nah, sir.
I had to go like this. And if we have some ones coming off to the side here, um, would it be in this direction? This one over here, is this correct?
Yes, sir.
Yeah, because remember, it will always go, it will leave north to go to south in a sense. So north to south. And Jadon, would this be correct? For south?
No, sir.
Nah, it'd be going to south. So, like that. Right, so let's look at magnetic induction, and I would have talked to you guys about this already, right? So, give us a read from Jadon. Get a read from them.
When a piece of unmagnetized magnetic material such as iron touches or is brought near to the pole of a permanent magnet, it is attracted to the magnet and becomes a magnet itself. In other words, the material is said to have been magnetically induced. It should be noted that only three metals can be magnetized.
You understand that?
Yes, sir.
So like, okay, I teach all this some extra, right? So what happens is in a magnetic material, you have dipoles. And under normal circumstances, the dipoles are in this array. When it encounters a magnetic field, the dipoles actually align and become magnetic. That's what's actually happened. So the magnetic, so like let me ask you that question. Is there any wires or is it like a wireless process? Like, can you see the magnetic fields?
Yes,
Right.
sir.
You can see it. Like when you have a magnet in your hand, you see magnetic field lines.
Oh, no, no, no. I thought you
No,
were talking
you don't
just
see that, right? You don't see that.
body
You
journey.
don't see it, you don't see that. So the magnetic field lines are invisible. And if you have the magnets close to iron, and it technically inducing the magnetism on the iron, because I think about it, Jadon, the magnetic field lines are invisible and they extend around the magnet. Isn't that what's causing the dipoles to align? Isn't that what's causing it to align?
Yes, sir.
Yeah, and that's done wirelessly. So that's like induction. Induction is any process that happens like wirelessly. You could think about it like that. If there's like no physical contact, then that's induction. So let me give all a better one than that. Because like let me give all a better one for magnetic induction. Right, give me a second. Let me just verify what's in is correct. Most likely this is correct, but I just want to make sure. Uh, okay, yeah, I was correct. Cool. Because that's my favorite course in UB. I was better, right? Yeah. You just have to make sure. So long story short, guys, dipoles is just like small magnets. Like all magnetic materials, they have dipoles, right? And like dipoles is like small atomic magnets. And all this see for itself, like under normal circumstances, there's being disarray. If you bring a magnet close by, the magnetic field wirelessly causes it to align and act like a magnet itself. Right? So in an unmagnetized, I'll give only like a long thing and then like a simple thing to write. So in an unmagnetized magnetic field, the magnetic domain, the magnetic domains, like let me ask a question. So the magnetic domains is the dipoles, right? That's the dipoles. This is the dipoles. What do they do? Like let me ask a question. Do all of them point in one direction or are they in disarray?
Sorry.
Right. It's not exactly dipoles. Like if we being very correct, a magnetic domain is more so the region containing a number of these atomic dipoles aligned in the same direction. So like let me explain. The dipole, guys, like the dipole is a really small atomic magnet. And like all magnetic materials, they have like these small magnets. But typically these small dipoles, they could be in disarray. Now the magnetic domain is a region containing a large amount of atomic dipoles aligned in the same direction. That's what it is. Right. So in an unmagnetized magnetic material, the magnetic domains point in many different directions. So guys, long story short, magnetic domain just means a bunch of dipoles. That's all. That's all. It just means a bunch of dipoles. A bunch of small magnets. Yeah. In many different directions. So question, Jadon, if you have a bunch of magnetic domains pointing in different directions, what happens to the magnetic effect? Would it be strong or would it cancel off?
It will be strong.
Nah, like all of them in different directions. Like think about it. If you want to pull a car and a bunch of people pull in different directions, will that be useful?
No.
No, if you want to pull a car and everybody got to pull it in one direction.
Yeah.
Guys, that makes sense, right? Think about it. If you're pulling a car, Ryan, Drew, Zachary, if you're pulling a car, right? Will everybody be pulling the car in different directions, or will all of you guys concentrate your efforts to pull it in one direction?
They concentrate the efforts for one direction. So
Exactly. So like over here, the magnetic domains, they point in many different directions. So if that's the case, will the magnetic effect be strong or weak? Tell me,
we
Jada,
Weak.
right? So the magnetic effect, um, more or less cancel off. then the magnetic effect cancels off. So which means they're weak. However, when a magnet, so when a magnet is brought nearby, its magnetic fields causes many domains to align. So Jadon, what's saying is like, so Jadon, enter magnet has magnetic field lines.
Yes, sir.
So when you bring it close to the unmagnetized magnetic material, the magnetic domains would now what?
Induce the
You know?
material.
No? Okay, so the magnetic domains is just a bunch of these small dipoles, right?
Yes, sir.
So what I'm saying is like the dipoles could be in disarray, right? They could be like all over the place.
Yeah.
Me saying magnetic domains just like on a larger scale. So it come like I saying 1,000 dipoles.
All scattered.
Yeah, like in a larger scale. So
Alright.
like all magnetic domains is it just means like it's a bunch of dipoles. It's like a
Just,
bunch of dipoles in the same direction. So like in the ion, you have like a maybe like five dipoles going in the same direction. No, that's a lie. Maybe like 1,000 dipoles going in the same direction. We're talking about real dipoles, inside it. So maybe like 1,000 go be in the same direction, 1,000 go be in the other direction, 1,000 go be in the next direction. So magnetic domains just a bunch of dipoles in the same direction.
yes,
And
sir.
and what's saying is, Jadon, in the ion itself, you have a bunch of different magnetic domains. You have a bunch of magnetic domains. So like magnetic domains is just dipoles in the same direction. In ion, you have a bunch of dipoles. And like some dipoles go have the same direction. So you group them together and you see that they have a magnetic domain. Now in the ion itself, you have a bunch of different magnetic domains. So what's saying is normally the magnetic domains they point in many different directions. So Jadon, if the magnetic domains pointing in many different directions, what happens to the magnetic strength in many different directions?
It will be weak.
It will be weak, right? But if I bring a magnet nearby and it causes the magnet, okay, so the magnet has magnetic field lines, right? And the magnetic field lines would cause those magnetic domains to align. So if the magnetic domains align now, what happens to the magnetic strength?
It will get stronger.
Exactly, because now they align and they come like everybody pulling the kind of the same direction, in a sense. So when a magnet is brought nearby, its magnetic field causes many domains to align, right? If that is the case, then the material develops magnetic poles and behaves like a magnet. And I mean, you guys saw this for yourself. Let me get a diagram real quick. Yeah, so like all this for itself, right? Like, so like, okay, Jaden, just to make sure you're not confused at all, guys, this magnetic domain might be confusing you all, right? So let me explain. So Jaden, when you look
Yes,
at this, right, you see how you have this, they're going in the same direction?
no.
No, like, yeah, they are, watch.
Oh, yeah, yeah, yeah.
Right. The magnetic domain, Jaden, you
Yes,
would
sir.
you would count how much of those it have, and they would group them together, and that would be one magnetic domain.
Yes, sir.
And then like maybe this. So like if you look, you have this, and you also have this. They're in the same direction, so they would be the same magnetic domain.
So just group all the things that
Dipoles, all the
direction.
dipoles, say it correctly. You would group all the dipoles
Yes, sir.
that,
You're given all the dipoles
in
in the
that
same
have the same what? That have the same what? That's what O.
um O
Yeah. Or E.
orientation.
Yeah. So like all the dipoles with the same orientation, you group them together, and that would form its own magnetic domain.
Yes, sir. I understand.
Yeah. So like in any unmagnetized magnetic material, you'll have a bunch of different magnetic domains in different directions, and that will kind of cancel off the magnetic strength. But like if you bring a magnet close, the magnetic field, it causes them to align now. And when it aligns, it develops like a pole. So like this could be south and this could be north.
Yes, sir.
So that's like the whole concept. And that is what magnetic induction actually is. Right? That's what it actually is. Let me give you a simple one though. But right then, a C6 exam, people could be like, what? How the hell are they know that? It's crazy. Long story short, give you a simple answer. So magnetic induction is the process. So like all I had to understand, so Jaden, Zachary, Drew, Ryan, like okay, anytime you hear the word induction, just know it is without contact. It is without contact.
Yes, sir.
Drew, do you have to okay, like does the magnet have to touch the iron for the iron to experience the invisible magnetic fields?
No, sir.
No, so like the magnetic field lines exist around the magnet. And so if you have an iron like in a close proximity, it don't have to touch, but the magnetic fields would cause the magnetic domains to align. So magnetic induction is just simply the process by which a magnetic material becomes magnetized when placed in an external magnetic field. All you agree with that? Like everybody agree with that? Like this is not complicated, right? Like let me know if all you understand this.
Yes, sir. I understand.
So Ryan, when you hear the word induction, induction must be with like you tell me, induction happens what?
When something becomes a magnet.
Not quite. Anytime you see the word induction, just know it is without direct contact. Without direct contact. So I was saying, Ryan. So Ryan, a magnet. Doesn't a magnet have invisible magnetic field lines around it?
Yes, sir.
So do you have to touch the magnet to the iron for the iron to feel the magnetic field lines? Mm,
Yeah.
No, let me say that again. Ryan, around the magnet, what you have?
Magnetic forces.
Nah, say magnetic field lines. You have magnetic field lines. And so, do I have to touch the iron to the magnet for it to experience those lines? Like, imagine you have a piece of iron here. Right
No.
now, would you say the iron is experiencing the magnetic fields?
Yeah.
Yeah, because then you see the magnetic field touching it.
Yeah.
So Ryan, do you have to touch the iron to the magnet for it to be magnetized?
No.
No, it can happen wirelessly. Why? Because the magnetic field lines extend around the magnet, and that would interact with the iron even if it's not touching it. You dig?
Yeah.
Right, so wait, let me just finish this. Magnetic induction is the process by which a magnetic material becomes magnetized when placed in an external magnetic field um, without direct contact. Yep. So Ryan, read that for me.
Magnetic induction is the process by which a magnetic material becomes magnetized when placed in an external magnetic field without direct contact.
You understand also like you could have a magnet around the magnet, you go have magnetic field lines. You go have the magnetic material. The magnetic material go like it go feel the magnetic fields and the magnetic domains go align and they become magnetic.
Yes, sir.
That magnetic domain part is confusing, yeah. When I say magnetic domain.
No, sir.
Nah, I'm gonna go over it anyways. So like this is higher level, right? This is like tertiary level. But I'm showing on it anyways. So Ryan, in all magnetic materials, you have these things called dipoles. You see these little things over here looking like pills?
Yeah.
All of these are dipoles, and it's like they come like small magnets. They come like tiny atomic magnets that make up the material. So Ryan, right now, the dipoles in the same direction or like in different directions.
In different directions.
Right. So here's this. You're probably wondering, so what is a magnetic domain? A magnetic domain is when you group together, all the dipoles are going in the same direction. So like this and this, see how they're going in the same direction?
Yeah.
I'd group them together and I'd call that a magnetic domain. So like if you notice you have multiple magnetic domains, so you have like those two going in that those three going in that direction, then you see in this and this, they're going in that same direction. So like in any given magnetic material, Ryan, you'd have multiple different magnetic domains. But the point is, Ryan, if it is unmagnetized, those magnetic domains, do they point in the same direction or are they in disarray?
In this area.
Right. And when you bring the magnet close by, what does the magnetic field do?
They make they make all of them look in the same direction.
Right. So it causes the magnetic domains to align. That's the proper way to say it. And if the magnetic domains align, what will be developed?
A magnet.
Yeah, a magnet with poles. I was looking for poles. What develop is as a North Pole and a South Pole. Yeah. So Ryan, I'll wait to read everything to make sure you have it locked in.
In an unmagnetized magnetic material, magnetic domains point in many different directions, so their magnetic effects cancel off. When a magnet is brought nearby, its magnetic field causes many domains to align. The material develops magnetic poles to behave like a magnet.
You understand that fully, right?
Yeah,
And you understand the simpler one, I presume.
yeah.
Nice. So Drew, how you feeling? You good?
Yes, sir. I good.
You sure?
Yes, sir.
Okay. So that's we call our day. So today, let's review what we looked at. So what did we look at today? Well, I showed you guys what magnetic induction is. We looked at what a magnet is. We looked at ferromagnetic, diamagnetic, and paramagnetic materials. Yeah. And we also looked at, I remember, we also looked at today.
Capacitors.
Those say capacitors, eh? But we're long, yeah.
Capacitor. You know what I'm talking about.
Capacitors. So we looked at capacitors. What else we look at? We look at what?
Transformers.
We barely look at transformers. What was the main thing we look at
Mhm.
today?
Diodes.
Yes, diodes. And we was using diodes to do what? What were we using diodes for?
To convert to AC to DC.
Yes, that is it. What type of how much types of rectification did we learn?
Two,
Two. Which one is better?
full wave rectification.
Right, because why? Why is it better?
Because it does work in the positive and the negative.
Say the proper thing for me. Positive and negative what? I see you, Zachary. Yeah, I think you have a camera on. You know, Zachary, I didn't.
Oh shit.
You
I
already look
sat
like
on my camera by accident.
you already look like Kendrick, you know. Yeah.
Nah, sir.
Oh, Maki camera there.
Nah, sir. I get.
Are you feeling chopped this morning?
Yes, sir.
Aren't we all chopped?
Hmm. But yes, sir, positive half wave and
No, no,
negative
no, no. Positive
half
half cycle.
cycle. Yes, sir. And negative half cycle.
Yeah. So the full wave rectifier is good because it conducts during the half wave cycle. I mean, the positive half cycle and the negative half cycle. So there's no gaps, right? No gaps. How much diodes does a full wave rectifier use?
Four.
Four, right? A half wave rectifier only uses one. But what's the problem with that? What's the drawback about a half wave rectifier? Ryan, Drew, Jada, no, like it's what's the drawback?
It's not constant. Is stop and then start back.
I way to say that a bit more, say that a bit better. Say that a bit better for me.
That it only conduct during positive half cycle.
Exactly. Yeah. So there's periods of downtime. So if they ask you for a drawback, you'll say the half wave rectifier only conducts during half the operation, i.e., during the positive half cycle. So there's a period where there's no current. Yeah.
Yes.
Cool. So are you feeling good about everything we say?
Yes, sir.
Yes,
Nice.
sir.
So guys, I will see you all in the next session. Hopefully we'll be less sleepy. Like I literally, I ain't gonna lie, I ain't gonna cap. I wake up and just start class. That's how I do.
I will back and sleep now.
Same, I'm gonna go back and sleep. Take care, guys. Have a good day. Later.
Mhm.